Here are solutions to homework set number 11 for ECE 341. And this homework set we're looking at Markov chains. Now the first problem is kind of a classic problem in Markov chains. I've got 4 people playing hot potato. If A has the potato, 30% of the time A keeps it, 20% passes it left, 50% of the time passes right. If B has the potato, 40% times keeps it, 60% passes right, and so on. Problem 1. Assume A starts with a potato. What's the probability that each player has the potato after 10 tosses? Well, to do that, I set that up as a discrete time system. So this is after k tosses. This is the transition matrix relative to k. So what this says, if I look at the column, and this is column for A, B, C, and D. If A has the potato, 30% of the time A keeps it, 20% passes it to B, 50% passes it to D. If B has the potato, 40% of the time keeps it, 60% passes it to C. If C has the potato, 10% time keeps it, 50% passes to A, 40% passes to D, and so on. If you add up the columns, they should all add up to 1. That's one way to check your answers. So doing that in MATLAB, here's your state transition matrix, call it M. This is the probability that A, B, and C, D will have a potato given where the potato is currently. If initially A has a potato, the initial condition is 1, 0, 0, 0, so A's got the potato. After 10 tosses, that's just take this matrix to the 10th power times x0. That's the probability that A, B, C, D have the potato after 10 tosses. Problem 2. Assume A starts with a potato. Determine the probability that A has a potato after k tosses using Z transforms. In that case, I put this in state space form. I've got x of k plus 1, or Zx, is A times x plus B times U. In this case, that's my initial condition. And y is the state that I'm looking at is C times x. So my A matrix in state space form is my state transition matrix M. My input is the initial condition x0. C is what I'm looking at. I want to find out the first player has the potato, that's A, and D is 0. This is your sampling rate, 1 second, 1 toss. Input that into MATLAB, find the transfer function, and that's g of z. When you do this, I'm always off by z. So that's actually the Z transform of A. So, once I have A of z, I can find A of k. Do partial fraction expansion. So here's the term over z. Actually, pull out a z first. Take the partial fraction expansion, the term over z minus 1, second term. Third one, you add a complex number. Fourth one, complex number. Take the inverse Z transform. This is 0.1245. 0.45 times 0.13 to the k. Double that, 0.43 times 0.44 to the k. There's how fast it oscillates, 65 degrees per sample. And the phase over the negative term is the correct one, plus 12 degrees. So there's A of k. As k goes to infinity, all these terms go away, and I'm left with 12%. Problem 3. Repeat using eigenvectors. Well, in MATLAB, if I take my A matrix, the state transition matrix, find the eigenvectors, eigenvalues. These are the eigenvectors, these are the eigenvalues. The initial condition is determined by the excitation of each eigenvector is determined by the initial conditions. So multiplying by the inverse of m, there's your answer. If I look at the first eigenvector, this is the one that tells the steady state. This is excited by 0.55 times the eigenvector times the eigenvalue to the k power. So there's your steady state solution. All the other terms, there's the second eigenvector times its initial condition times its eigenvalue. Third eigenvector times its initial condition times its eigenvalue to the k. fourth eigenvector is the initial condition, eigenvalue to the k. So all this together is A of k. That's another way of finding it using eigenvalues and eigenvectors. Problem 4 and 5, look at absorbing states. Suppose two players are playing n games. For each game, A has a 40% chance of winning, 25% chance of a tie, 35% chance of losing. In order to win the match, you have to win two games. I'll be up by 2 games. So the states are, I'm up 2 games, the match is over. A is +1, even, -1. B is up 2 games, match is over. The Markov chain for that is this. If I'm up 2 games, A is 1. That's an absorbing state. If B is up 2 games, B is 1. That's an absorbing state. In the middle, if A is up 1 game, 40% chance A wins, goes up 2. 25% chance tie, still +1. 35% chance loses, goes back to even, and so on. To find out the probability A wins in 10 games, input this matrix. Here's my initial condition. I start out at even. Here's my initial condition 0, 0, 1, 0, 0. Start out at even. Multiply A to the n times x0 times c. C is player A wins. And I get A cannot win in 0 games, can't win in 1 game. In 2 games, 16% chance of winning. 3, 4, 5, 6, 7, 8, 9, 10. That's the probability A wins after n games. I can do that using Z transforms. Given the state transition matrix, the initial condition, C is 1, 0, 0, 0. I'm looking at player A. D is always 0, sampling rate of 1. Input that into MATLAB, find the transfer function, times Z, and that is A of Z. To find A of K, take the inverse Z transform. So here's the Z transform, pull out a Z, do partial fraction expansion. So there, pull out a Z, do partial fraction expansion, take the inverse Z transform, first term, second term, third term is 0, fourth term. That's A of K. Same answer we got before, but here's the closed form solution for it. Also says that as K goes to infinity, A has a 56% chance of winning the match. Finally, here's a harder one. Tennis is actually kind of a complicated game. In tennis, you have to win 4 games and be up by 2. So if A winds up winning after being up 3-0, A wins the match. If the match is at 3-1 and A wins, A wins. If A is up, A wins the game after going 3-2, A wins. Otherwise, if we're ever at 3-3, it enters the Markov chain. I've got to win by 2. So to calculate the chance that A is going to win the match, I need to calculate 3 binomial distributions that are Markov chain with conditional probabilities. So, start with the first one. The probability that the match goes 3-0 is in 3 games, A wins 3 times. Probability that A wins, A loses, 27% chance the match will wind up at 3-3. 3-1, 3-2, 3-3. If I'm at 3-3, I enter a Markov chain. So here's the state transition matrix. Take that to a large power, like 100. After 100 games, 100 matches, 77% chance that A wins, 22% chance B wins, very small percentage chance the match is still on. So that's the chance that A wins, given that you enter 3-3. All right, the total chance that A wins is your conditional probability. Probability that A wins, and you went 3-0, plus probability that A wins the next game, given that you're at 3-1, plus the chance that A wins the next game, and you're at 3-2, plus the chance you're at 3-3, and A wins a tiebreaker match. Put that all together, and I get 82%. So the chance that A wins a game of tennis is 82%. With a fairly complicated format, it's first to 4 games win by 2. And that is homework set number 11.